I'm Eddie. Are you guys tired after the previous lectures, or have some energy left? Fresh. One more. So it's good to be here. Thank you, Kostya, for inviting me a second year. Last year, Kostya convinced me to come and give some lectures in the seminars. And this year, even more, I'll give you later in the course some lectures on like advanced topics in computer vision. Stuff like image segmentation, pose estimation. Maybe we'll get to how to work with video. But today, we're going to talk about a topic which is very dear to me because a lot of our time as researchers or engineers goes into it. That is how to work with scientific papers. It's something that nobody teaches us to do, not in university and not in industry, and yet we spend a huge amount of our time doing it. By the way, I love the idea of this course, of the YDSA, because I can tell you from the industry there's just a huge shortage of engineers, of researchers, of people who understand data science and deep learning and machine learning in general, and academia just is not enough. It's not putting out enough talented people, and to be honest, today I'm not sure if academia is the best place to learn, like a course on deep learning. There is excellent material online. This is a great place, and I personally know Omri and Kostya you're in good hands. This will be good for you. So, by the way, this is not a lecture I often give. This is like the second time. So feel free to interrupt if something is unclear, and generally it's meant to be as a discussion. It's not a heavy topic. So, okay. So, what's the motivation to even talk about this? So, in your career, like ignore academia for a second. In your career in the industry, there will be a repeating pattern where someone gives you a difficult problem and hopefully interesting. And basically, you don't want to start from nothing. Right? If it's a deep learning problem, you don't want to reinvent the whole architecture and build everything from scratch. So usually what you do at this point is you ask yourself, what is the closest problem that I know others have already solved? We're sort of like math people. And that can be something similar from a related field, or even in this field, there is many different approaches, and I want to survey them and choose something that is most like what I need. And after you do this process, you want to try to apply these solutions that you've already found to your problem, to fit them to your needs, to switch things up, and to start iterating. And my point here is that this step 3 of searching for the solution that somebody else did is a really, really important part of the process. And usually people do it quickly, and then they spend a lot of time working very hard to sort of compensate for starting from a bad starting point. But in my experience with deep learning projects, and I'm going today to talk specifically about deep learning, but I think it applies generally, it's very useful to invest more time than you think. Like it's rarely a mistake to invest a lot of time in the phase of finding your jumping point and really evaluating the different solutions and learning from them. There is a reason that they have succeeded. The other more urgent reason to learn to work with papers is that you're going to have to present papers in the seminar. So if that's a better incentive, you can have it. So a little bit about me. In my life, I've read hundreds, I think maybe thousands of papers, mostly in computer vision, specifically in the last few years in deep learning, as you can imagine. It's the sort of thing, it's funny, I'm on the air now, but it's the sort of thing while other people sort of sit in the bathroom and play games, I browse archive and see the latest headings. And basically my story is that we had a computer vision startup. It was called Visual Lead. I was the head of research there. And in about 2017, we sold it to Alibaba. And we've basically, in the last 2 years, been opening the Alibaba R&D Center in Israel, which is now grown to about 40 researchers. So it's an R&D center, but mostly focuses on research. It's sort of like the group is the AI research, part of the AI research branch of the global Alibaba company. So like Google Brain or Facebook AI, the equivalent to that. And it's like, I don't know how much you know about Alibaba, but it's similar to Amazon in that it has a lot of technology inside. For example, it's one of the biggest cloud providers and the fastest rising. But I've left Alibaba a few months ago to create a new company and doing automation in agriculture. Basically, imagine greenhouses where today a huge part of what's happening there is people doing manual labor, like harvesting fruit. By the way, we're talking about vine vegetables like tomatoes, cucumbers, peppers, basically your salad. And a lot of time there is spent on harvesting, on removing leaves, on pruning, on working with the flowers. And we want to basically build a robot that will move around the greenhouse and do that automatically. It's a very tough problem. It's a wild, it's a wild place, so plants they're unexpected. So you can imagine there is a lot of computer vision involved, of course, robotics and control, and hardware. So this is where every iteration of my career, academic papers, and me meet. So just some visualizations. On the right side is an example of an algorithm we have now in the agriculture company, where we do sort of segmenting of the branches and identifying, if you can see here with the light, the small points of identifying where branches leave the stems. And this is sort of a deep and multi-layered understanding of the plant. And on the left are like blog posts from the last few years that I wrote. Maybe this one is most relevant to today, finding and managing research papers, a survey of tools and products. As you can see, I was interested in this topic even before meeting Kostya. So this is about me, and now let's talk about you guys. I want to try to understand what's the what's the distribution of people here in terms of working with papers prior. So if you can, it's going to be like 3 questions. So if you can raise your hand if you have read at least 3 scientific papers in your life. Perfect. What about, no, keep it up. What about 15 papers? So, okay, most of you, like, I guess, have at least a bachelor's or graduate degree, right? Have you ever published a scientific paper? Okay, cool. Finally, have you been abroad in the last few weeks? I'm just asking. Just asking, yeah? Because there is just no reason, you know. So, reasons not to listen to me today, by the way, are that in every scientific category, things are different, especially when it comes to papers. The consensus is different on how to write papers, what are the guidelines, and of course how to read them. By the way, arXiv used to be only for physics. You know when I say arXiv, what I mean, right? So, yes, the website arXiv where all the papers today are published. It started as something just for physics, internal in no. Cornell, yeah. And to this day, they are basically stuck having to supply all the demand of all the papers and all the different fields. They don't really want that. They're just physicists. But everybody uses their website and what are they going to do? But if ever you ask yourself why arXiv still hasn't got a facelift after like 30 years, it's because they don't want to. The other reason is that this is just based on my experience and my peers. And everybody learns differently. So use common sense, do what works for you. Today I'm just going to talk about what works well for me and the teams that I worked with. So what are we going to talk about today? We'll present the basic anatomy of a paper. We'll be quick about it because I see that everybody here already knows that. I'll present what I think is a good way to think about how to read a paper in 3 circles and 3 levels of reading, and what sort of flow that creates. I'll try to convince you to apply critical thinking to reading papers. A sentence I want you to go out to have in your memory today when you go out is lies, damn lies, and deep learning, right? It's true. Then I will present some tools and resources that will help you to find and manage papers. And here I believe even the people who have already published stuff will see some new things. In the end, I'll also talk about habits that you can cultivate to keep up, because it's really, really difficult today to keep up with the onslaught of papers. Just so many things are published all the time. Even if you narrow down to a small field, it's like sometimes a few papers a week. And it just takes a huge amount of time to stay up to date. And I'll give you some basic tips for how to present your seminars, which are upcoming. So paper anatomy, I'm going to be quick about this because you guys know. There's title, authors, abstract, where there's like a short summary that the authors wrote. And the goal there is not always to make it as clear as possible, but to make it accepted to the conference. There's an introduction where usually sort of you're giving the background of the whole field of what other papers are doing, what are the common methods, what are the like data sets, and what historically happened. This is usually very good for background. There's the main body, where basically in deep learning they say, this was our problem was this, and this is how we solved it. This was our architecture, this is the kind of training that we did, these were the hyperparameters, these were the GPUs, and these were the experiments that we did and what we learned from them. There's also math in this part. And most people just jump right here when they start reading a paper, but I think it should be one of the last places that you look. I'm getting a very unresponsive. Okay. Yeah, so there's more parts where you get the benchmarks and comparisons to the state of the art. Discussion, where usually that's where the authors sort of analyze the results for you and what they mean and what are the implications for the field. Conclusion, which is basically a summary again, and references where they link to previous papers. Appendices, which is often overlooked, but especially in deep learning, this is where a lot of papers will reveal their secret sauce. This is where the sort of magical stuff that happened before is explained in detail, and if you really want to implement the paper, a lot of the time you really need to focus on that. So, the 3 levels of reading. I think of it in these terms. Basically, when you have a paper, you can skim it, you can read it, and you can own it. Right? And you can't do one without the other. It always goes in this direction. And when I say skim, what I mean, it takes a few minutes. And in the end, my test is, can you explain what the paper does, like what the paper says in 2 sentences? Can you do that? It's not trivial. A lot of papers are very unclear, and it's very hard, even after reading them fully, to say in 2 sentences what's the thing here. But when you skim, that's all I want you to be able to do. After that, and skimming should allow you the option to decide if it's worth to read on, right? Don't just jump and spend a lot of minutes or hours fully reading the paper. First skim it, understand if you want to invest the time, because a lot of papers are a waste of time. Reading takes usually hours. If you're familiar with the subject, it could be half an hour, but if it's a new field, it will take you hours, sometimes days. And after you finish reading, you should know like the goals, the background, and the methods used and the results. You should be able to explain it to a class. So when you'll present your seminars, basically you'll do reading. You'll be good enough to explain what it does generally, but there will be questions that you don't know how to answer and that you will not remember. And finally, owning. This applies in actual industry. Like when you want to take a paper and then improve on it, or use this method and apply it to your own problem, this is the part where you have to own it. And by owning, I mean that you actually are able to implement it yourself, where you look at the code and it's familiar to you, where you start finding mistakes just because you know everything, where you start thinking about improvements. And I really don't think that you can jump from reading to doing your own thing in the domain without owning the paper first. So for example, if you're basing your work on some paper that does something like detection of vehicles from satellites, and you need to detect not vehicles, but I don't know, football fields. I really recommend that before you start tinkering with stuff, first you see that you can reliably reproduce the results of the original paper. Because if stuff won't work when you try to identify football fields, you will not know if it's because of something that you did or because of something that basically you didn't even manage to reproduce the previous work. Always do it one step at a time. And to go a bit deeper into each of these steps, so as I said before, the flow is usually to skim, to read, and to own. And the thing to remember here is that reading a scientific paper is not a linear process. So to take it as a book and just read it linearly, I think it's the wrong way to go. So what do we do to skim? What do we do in a few minutes? We look at the title and the authors. The authors are usually useful because you can see what other things they do, what's their domain. Maybe you know them already. The date, especially in deep learning, it's important to see if stuff is recent or not. You can really get confused if you look at older stuff. Abstract, of course. The headings, just to get a sense of the structure of the paper and know and be able to understand what you'll see if you read more deeply. And a glance at the figures and tables. I find that this helps me most of all because usually at this point in our culture in papers, the abstract usually is also visual. You always have this one graph or one image that sort of explains the whole paper in the first 2 pages, and it's very useful. For full reading, there's more to do. Always skim first. Never just jump into a paper head-in. And if it's a new topic to you, if it's in a new field, I recommend to spend time reading the introduction. It will really get you involved into what's up with what's the state of the art, what's happening, what are other papers doing, and so on. And it will help make sense the rest of the paper. Then go to the figures and tables, and from here, I recommend just to have the following strategy. What is the minimum that you have to do to understand what this paper is about? That's what you need at this point. Like there is a lot of useless information, of details, of proofs. Don't just read like a robot. Think what's really is interesting to me. And what I find is that, for example, jumping to read the conclusions and the results is more helpful at first than actually reading the methods and the main body. I just want to see what was the problem, what's the background to it, what did they achieve, and by looking how they sort of measured themselves, it really helps me understand what I'm going to see in the main body. And only after all that, I think you should go to the main body and read the algorithms and such. And then, don't go too much into the details. If you want, you can do it later, but first try to have a good understanding of the paper. And then, I think most of the time you sort of need to reread it just to figure out all the small questions that you had along the way. And my big tip for this part is to use a notebook to write notes with questions that you would have liked to ask the authors or terms that you didn't understand. And in the end, like if for skimming the question was, can you explain it in 2 sentences? For this part, I would say, can you summarize it for me in like half a page or a page from your head, right?
Sometimes when you need to solve a new problem, you want to read multiple researches about it. So would you recommend to do it each document at a time, or maybe to do some, read in parallel, maybe, for example, the conclusions and then to understand the methods?
It's a good question. Usually what I do is I skim a bunch of papers and then I decide which one is worth to get into in more detail and start alternating between them. But when I'm in the reading mode, I just read the one paper because every paper has their own sort of style and their own train of thought. And if you switch in the middle, you sort of lose it. Even terminology can be sometimes different between papers. So I skim a bunch and then I have a sort of overview of the field in my head, and then I decide which ones to dive in, and usually it's multiple papers. And for the next part of owning it, which I think takes days, maybe even weeks, it's like this is actual work. You need to get into the code, you need to debug it, you need to make sure it runs on your computer, you need to tinker with the losses and the architectures and the data loaders, and that's where you start to actually be able to change things and to apply them to your own problem. Before that, you just feel like you understand, but really you don't. And it sort of reveals itself quite quickly when things go wrong and you don't know why. So at this part, this is where I have read supporting material and references. So when you're actually getting to the owning part, there is no avoiding that. You need to understand the ecosystem. Like usually a paper will explain some stuff, but it's based on a previous paper, and that one explained like the previous stuff that you also need to understand. So that's the point where I would expand and also read like supporting material. Yeah, so in my opinion, to own the paper, you actually need to be able to reproduce it. And naturally what comes from that is that you can debug stuff that happened there. Sometimes you will find things that will not make sense, and it will only not make sense when you understand it, right? So that's sort of the moment you know, okay, I'm in control now.
I have a question.
Yeah.
What if you don't have the resources to reproduce it? Some papers are on big architectures or whatever, and you don't have the resources.
So what do I mean by reproduce? There's two situations. One, when you don't have the code. It happens less and less now. It was horrible in like 2016 where there were a million papers and they didn't release the architectures. So when you don't have the code, I don't really think you can own the paper until you actually wrote the code. It's an illusion to think that you understand what they did, because you will not be, especially in deep learning, so many things are based on the small details, like small decisions about hyperparameters that they made, and sometimes they will intentionally not reveal them in the paper, so you can't reproduce their work and publish the next paper before that. So in that case, I think it will take you a lot of time. But if there is a code, then usually I don't see what's the problem. You would need like a single GPU most of the time.
Okay, so you're talking about like these low-level stuff, not like big architectures. You need big resources, like cloud services or whatever to reproduce stuff.
So like the only papers I can think of that actually need big cloud services is maybe neural architecture search, like NASNet and stuff like that. That took the order of 3,000 GPU days. But by the way, today newer works, they require like 4 GPU days, so you can do it in your home. But most papers, like if you look at the big architectures like ResNet, GoogleNet, that's the old ones. Today there's like EfficientNet and stuff like that. You can fit them on a single GPU, and you can even do it in like Colab or something with Google. It's not a big task, but without it, like if you don't have the compute, then you can't own it anyway. I mean, we're talking about the point where you actually have an assignment at work, and someone gave you the resources, and now you need to make something more from it. And I think you have to go through these steps. Oh, I'm already in the next slide. Yeah.
One out of how many things that you read do you actually find that you end up owning it? Meaning, if you read 100, how many of them do you end up?
A very small percentage. I'd think like 1 to 100 is a good approximation, and 1 to, like, my funnel is something like this. For a few years, today it's not the case, but for a few years I actually read every heading in arXiv under the title of computer vision, like everything. And I sort of had a mental filter that really allowed me to find keywords really fast. And only like 1 in 10 I would even read the abstract. And from those, only 1 in 10 I would read skim the paper. And from those, only 1 in 10. So it's a really small percentage. And it's it's an investment of days usually. And it's only worth it when it's actually related directly to the problem you're trying to solve or something you're trying to learn. Otherwise, I think just getting a general sense is good enough. Right, so here's the part where I'm trying to convince. Was there a question there? Yeah.
So how would you suggest combining between understanding the code and understanding the articles? So let's say I have an article and I need to understand how it works, and I also need to run the code. And let's say, you know, I managed to predict with the article, and now I'm working on training, but like with the code, but I don't deeply understand what's going on underneath. So how would you say we should approach it, to start with the code, start with, like, we have a general idea of the article, but not a really deep understanding of it?
Great question, and it happens a lot. This is like a situation which is usual. So what I do is I start from skimming the article usually. Like I do skimming. I do a small part here, small part here, and then I understand how to approach it better. So usually I would skim the article, see the figures and stuff, understand generally what was their purpose, what's their like new thing that they've added, and why does it get state-of-the-art results? Because everybody says they get state-of-the-art results, of course, and they measure themselves in horrible, horrible ways. But and then I go to GitHub and look at their page and start seeing the basic stuff. What are the requirements? What's the runtime? And how is it structured? And to be honest, I'm not talking about this in this presentation, but looking at the code is not less important than, like, looking at the structure of the code and stuff is very important. There's a lot of good papers that I simply refused to work with, to start off from them, because the code was horrible. Actually, in the last year or so, a big criteria for me when choosing, for example, you saw before that in the agriculture stuff, I did some pose estimation, right? And I need to start from somewhere. So I opened a bunch of projects that do pose estimation, and some of them were really state-of-the-art, some of them were not. And you have like this balance of stuff that's really open source, tried and tested, a lot of people are using it, and it's on many platforms. And that's from the code perspective, but it's like 2.5 years old. Are you going to use it? Are you not? That's the sort of decision you have to make, because what you will start from will impact like the next 1 or maybe 1 year or 2 years of development, right? Because you will not just randomly switch to a different architecture, or not architecture, to a different framework of code. If it's in TensorFlow and that's where you started, that's where we're going. That's what you will continue with. So my criteria lately in the last year or so really became also the code. Is it a good framework to start from? If it's not, sometimes I just decide not to use it even if it gets amazing results. And the trick here is to find something that's both state-of-the-art and that you can work with the code. And something that sometimes I do, or we do as a team, is sort of take a code that's that sort of researchers built it for their one paper, and then you take a few weeks, and all you do is just make it robust, right? You clean up the bed coding. You add some hyperparameter control. You basically make the whole package more clean, and then new people can join, and the magic can start to happen. But before that, if you don't do that, you are doomed to suffer later on. So basically what I would say is think of the infrastructure. The beginning of each project, where you read about it and you choose which papers to use and you look at the code and you choose the repository and you fit it to yourself, it's critical part of the project. That most researchers, they just want to jump straight to the work. But if you don't do this, you will forever be unscalable. The best results, if I'm looking at what gets state-of-the-art results these days, it comes from teams that have a very good structure, very good infrastructure. And to me, deep learning is a lot about software engineering, and it really shines. That's why companies like Google and Facebook are the best at it. They are software engineers at heart, right? Here's where I try to convince you to apply a lot of critical reading when you're reading deep learning. As I said, lies, damn lies, and deep learning. This is like the estimation. It's been a long time, so the joke is probably dead, but this is an estimation of the world population and the amount of people attending NIPS. And the projection is that at some point there's going to be more people in the conference that are alive. And this is the better meme. The previous meme I wanted to use where this goes backwards. And here I'll just talk for a little bit about the incentives that are happening here. There is an actual explosion of the amount of papers that are being released in deep learning. It's impossible to keep up with. I think to the latest NIPS there was on the order of 10,000 papers submitted. Now imagine what this does to the reviewing process. Imagine what this kind of competition does to the scientists that are submitting papers. You are in such fierce competition that all you care about is just to submit the paper as quickly as possible and make it sound as convincing as possible, because otherwise you know that in like 2 weeks or 1 month someone else is doing it, maybe a few teams, and someone will just be ahead of you. And that incentivizes sloppy work and rounding corners. And on the reviewer side, reviewers are, at this point, a lot of them are just juniors. They're not like people who have had years and years of experience doing this, because there's too many papers. So the whole ecosystem is out of balance, and I don't remember which professor said it, but the best way to kill a science domain is to make it popular. And by the way, we can talk at another time about how AI can help here and so on, but for now this is a real issue. And let me give you like 2 examples from memory. In CVPR, which is the maybe most prestigious computer vision conference, there was a paper accepted, and it got like state-of-the-art results, and everybody was happy. Then 3 months later, some Reddit user said, so they wrote something in the article which sounded a little bit off to me, so I actually went to their GitHub page and tried to recreate their results. And I noticed that they have a problem in the way that they measure the results. So basically the way that they measure their test set is wrong. And they gave themselves like 10% more. Is it on purpose? Is it by accident? We'll never know. We do know that the guys were nice enough to reply in that Reddit thread in our machine learning and say, yeah, actually you caught us. That's a bad error, and we're going to fix it. And we're adding this to our paper. In retrospect, but the paper has already been displayed in CVPR, and many people looked at it and learned from it, and they now think that that's the way to build networks, right? So what do we learn from that? That no reviewer actually invested even 5 minutes to run the code in GitHub. So they could be writing one thing, the code could be doing something entirely different, and nobody knows. That's why I'm really serious about this. This is like not the exception. In my experience, this is the rule. Like most papers I worked with, and almost all papers I tried to own, always I at some point started going like, what the fuck, this is not aligned to what is written in the paper, the code is different, this does not make sense, and then you slowly figure it out. But just assume that you're being lied to, intentionally or unintentionally. It comes with the territory. Another example, by the way, is where I think in NIPS it happened, where they there was many submissions and they gave a bunch of reviewers to rank them. And then they took the same submissions and they gave another bunch of reviewers to rank them. And there was very, very little correlation between the results. So basically when you submit to NIPS, there is a lot of random stuff happening there. It's really, yeah.
I think maybe a better way to work with the scale or resolve this is to refer to crowd wisdom, I guess. Like you said, someone who never did that. So you think that's the direction, I don't know, this field will go into?
I agree wholeheartedly. I think you're gonna need both. Like you're gonna need the experts, but in my opinion, and this is just now we're in opinion territory, though I think we were already in a lot of what I said. Yeah, you're gonna need wisdom of the crowds. And I agree with you more than you think. Like about a year ago, I had this huge idea that we should do something that is the equivalent of IMDb or Rotten Tomatoes for papers. Or if somebody uses Goodreads, just imagine Goodreads for papers. But it's the sort of project where it's not easy to see how you monetize it, how you make money. It's only sort of pro bono, and it will take years to build such a community. So whoever here is willing to pick up the glove, I'm gonna help him and be the first one to sign. Later, I'll show a small demo of something that actually me and my friends have built, which is like the one building block out of many things that should be done, I think.
Most of the papers Regarding computer vision and machine learning in general from the academia or from research groups in the industry? And are they held to different standards when it comes to the data?
Same standards. I mean, there's a double-blind process usually where you don't even know who wrote it when you review it, though that's not entirely true because they always, sort of today, they're published in archive before they are submitted to the conference, so you sort of already know. So I don't think there's a different standard. About statistic, it's hard to tell. There's a lot from both. I would just go 50-50. I don't know which one is.
And they're of the same quality, usually?
No. What comes from industry is more reliable. It's usually it's not like the best papers have to come from industry, but if you see something from academia, there is a bigger chance that it's crap. And if it's from industry, very rarely companies will be willing to look bad. So when we talked earlier about good code, bad code, and we talked about looking at the authors, one of the first thing I look is if there is a big company behind it. And usually in computer vision lately, it's Chinese companies like Megvii or ByteDance, people behind TikTok. They do great stuff, and their code looks good. You can actually work with it. By the way, Microsoft is great as well.
What is the incentive of companies to release code that is good? I mean, if they have some groundbreaking algorithms, so they won't publish it.
That's a good question, and there's maybe even a deeper question here: is why is this whole ecosystem so open sourced? Why do you get PyTorch for free?
Self-advancement. Self-advancement.
That's what I think too. It works both ways. The engineers who get to publish works and papers and publish code online, they enjoy their work more. They feel like they're improving, and their reputation is improving. So they will go to the company that allows them to publish openly and showcase their work. And on the other side, the companies want you to use their ecosystems as much as possible. About specific projects, I don't really know. Why does Facebook release Detectron? I don't know what exactly is the benefit there for them, but they do it. Maybe just it's policy maybe it's just an internal policy. Hard for me to answer, but I'm happy that they do it.
And also, many times the data itself is problem, right? So if you just release some half of the data or use some small fraction, it doesn't help create the code.
True, but usually when you see papers, they are talking about data which is available. It's very weird to publish a paper about data that you don't put online or nobody has access.
So the paper versus what the company really has.
So yeah, you see stuff like with Google and Facebook, they have access to huge, unimaginably huge data sets. For example, Google has JFT, which is 300 million images or something like that. Which makes ImageNet look tiny, and they get better results on it. But whenever they publish a paper, they also show their results when they train just on ImageNet. So you can sort of still compare it. Yeah, and by the way, the industry standard is sort of first you release the code, then after some time you start adding the actual weights of the network, so people can reproduce the results and get the results locally, and usually the amount of delay is determined by how close they are to publishing the next paper. Because what they care about is that you don't use what they published to publish the next one before them. So that's the thing. Usually there is a delay of half a year. One more question, yeah.
Regarding frameworks, I know it's maybe a bit off topic, but is there a recommendation of what framework to use, PyTorch versus TensorFlow? I know that's a big question, but
I'm on camera, so PyTorch, yeah. I started with Caffe. I think my most famous blog post was about installing Caffe on some version of Macintosh. I fought with it for 4 days. 4 days just trying to install it on the damn computer. And when I finished, I wrote a huge blog post about it, and to this day, this is the most popular thing I've ever written. So, and after that came TensorFlow, and now PyTorch is finally something that feels like Python. It's very, very easy to get into. It's not like there is no chance of going back to TensorFlow, but to me, there is, like, I'll be honest, every project I did in the last year was in PyTorch. So some stuff to sort of questions you can ask yourself when you're looking at the paper. I'm just going to read this for you. So, did the paper present a valid and well-posed question? Does the paper answer it well? Does it try to be clear? Sometimes you can actually tell that there is very little new in the paper, and there is like you can summarize the paper in this one sentence, and everything else is so that they get accepted to the conference. Are the results supported by the conclusions? Are there alternative solutions which are really easy and they didn't consider them? Like, did they just overcomplicate things to show how smart they are? Were the experiments fair? This is usually, the answer here is usually no. Like, almost everybody does the experiment in a way that shows why they're the best. And were they results, and were they compared well? And so on. Okay, next to the next part, which I think will give value to the people who have worked with hundreds of papers themselves. Some tools to find and manage papers. And here I'll ask you to put your hands up again. So have you used Google Scholar? Okay. Have you used a reference manager, and do you know what it is? Okay, but less people. Have you written a paper summary online somewhere? Like, have you ever put a paper summary in your GitHub or? Okay, so in my opinion, the first and most useful tool is still Google. When you start looking for
ResearchGate counts or just for code?
ResearchGate counts, yeah. It counts, definitely. So in my opinion, when you enter a new domain, like a new field that you want to learn, or when you're looking for something, Google is still the best place to start. I usually just put like some keywords or the names of the paper there, and I find the easy stuff, the blog posts that explain the whole field, the sort of official or unofficial GitHubs that show some works, and you can just see some examples with your eyes and start to get a feeling for what's going on, what's possible, what's not possible. That's a good way to learn. And it's always useful when you're searching for a specific paper. If you put it in Google, you can, with like good odds, find some lectures on YouTube or slides that the authors distributed, especially if they presented in a conference. And also find online discussions and summaries through Google. Now, about reference managers. So what's a reference manager? Basically, it's a like paper library. Imagine that you're reading, I don't know, tens of papers or hundreds of papers. What do you do with them after? How do you keep track of what you've read, what you didn't read, what your notes are? Maybe even you do it as a group. So today, even professors that I talk to, what they do is that they have this huge folder where they just put PDFs inside, and they don't get the updates to the PDFs, and it's very hard to find anything later. And here, I hope you can still see what I'm going to show. So this is sort of what a digital library for papers looks like, right? Where you have a list of papers. On the left side, you have, it's like Gmail. You have folders and tags and stuff like that, and you can label your papers. You even have groups, so you can manage papers together in a group in work environment. That's great to have, because what I found was happening was that everybody was individually reading papers. They were not sharing the information to the point where people would read the same paper, have different summaries, and not share it with each other. They would not even be aware that they are reading the same stuff, but it makes sense. And now that you have these like hundreds or thousands of papers grouped up, just a double click and you get to open it, and you can put notes that others can see. It's very, very, very useful. I wish more people would use it. You can see that most of the papers I have now are about agriculture. Oh, I think I lost the slides. So I just showed you Mendeley, but there is many other competitors. Mendeley, by the way, is the evil one. I think it's unfortunately the best one, but it's the one by the bad corporation, while Zotero is like open sourced as can be. Paperpile is a paid version, but it's really, really good. I don't know that one, but
It's Java. It's open source.
awesome. So yeah, I'll look it up. Cool. Let's talk about more tools that I think nobody knows. Short Science. It's a place for summaries. Basically, when you start reading a paper, especially in deep learning, you can search for it in Short Science, and a lot of times you will see someone else who already posted a summary. They have thousands of summaries now. I can't say that they're like super hot and that every paper will be there, but the famous papers you will find there. And I recommend that if you like, a nice thing to do is when you read papers and you write notes to yourself, maybe leave a short summary there also. I think as a community it sort of helps. Open Review is a nice experiment for some conferences like NIPS or ICVL or like one of the ICLR, where it's basically like the reviews for the papers are online. You can see what the reviewer wrote. Everybody can see. And you can also, as a person, just write your own review or ask questions, and the authors usually answer. In some papers, this has been like a blessing. I could actually talk to people who did something and ask them a question and get a reply like the same day. This is great. Papers with Code is a great resource if you don't know it. Basically, it connects, it sort of finds in GitHub all the repositories which have a link to archive, and then connects the paper and the code, which is very useful. I think recently they joined Facebook, very recently. And also something new that they have is they actually track the state of the art in many different subdomains. Like if you care about I don't know, finding segmentation of cityscapes, which is a data set, then they have this category and they actually show you a graph of the state of the art like in history with links. It's super convenient. Semantic Scholar is what everybody who answered yes to Google Scholar should be using instead. It's the new Google Scholar. Google Scholar hasn't been updated for a long time, and Semantic Scholar is done by the good sort of companies, like it's the Paul Allen Institute for Artificial Intelligence. Paul Allen left a lot of money to charity after he died, and that's a great resource. It's basically Google Scholar with a lot of bells and whistles. They have a lot of NLP analysis of papers, and they suggest similar papers and stuff like that. Maybe the biggest database today. And in like 1 minute, tools for authors. So if you write a paper, then Overleaf is the sort of Google Docs for your LaTeX, I don't know how to say. It's collaborative, it's very easy to use. Authorea is like the new version. If Overleaf still uses LaTeX, Authorea is basically a WYSIWYG editor where you can just use it like Word, like a word processor. And what's nice about it is that it allows you to put graphs and the code behind that generates the graphs in line. And you can also start getting comments from people in line, and it becomes like a public experience of discussion. I think this is like the future of how papers will look. And CodeOcean is one experiment where they try to tackle the reproducibility problem, where you actually run the code on their infrastructure, and everybody can run it themselves on their cloud. I'm not giving it justice, but just look at it. It's a great experiment in how in the future submissions could look like. So, as you said before, we need more and we need better tools because this is sort of getting out of hand. We need a way to improve the reviewing system. We need to improve knowledge sharing. I think the way we rate papers, to like the signal that we have about if a paper is good or not is really, really weak. Like imagine there's 1,000 people read a paper and maybe 10 out of them actually write a paper and cite it. So most of the votes are sort of gone completely, and the people who are citing it don't necessarily mean that it's a good paper. They could actually be citing it saying it's a bad paper, but it still gets a citation. And sometimes if you don't cite a paper, the reviewer is going to later tell you, hey, why didn't you cite that paper, which by the way I wrote. So it's a very weak signal that I think we need to improve. And to improve how to find relevant papers and authors. We're close to the end, so let's talk about habits that will help you track what's published, what's going out there, because there are so many papers coming out. What's mostly helpful to me, actually in the last like couple of years, has been newsletters. There is a few newsletters specifically for deep learning. Here are the my 3 favorite, which every week will send you a curated list of the best papers that came out, of interesting interviews by like stars in the field, and basically news about what's happening. It kept me in the loop very well, especially if you have a few of them and each one of them has like their specialty. Another thing to do is to subscribe to arXiv with RSS. This is what I used to do in the past, but I stopped. There's too many papers now. I mean, I would need to sit in the toilet forever. The third one is to use Semantic Scholar or Google Scholar to create keywords. So whenever you find a paper that you like, that's interesting to you, tag it as a paper that you will get alerts for when new papers cite it. Or when you find an author that you like, you can also tag him and you will get an email whenever he publishes something new. And what's nice is that when there is like a combination of a few alerts going off together, it will also be apparent in the email. So I don't get a lot of notifications from it, but the few that I do are almost always very, very, very useful. These are the methods that I'm using today. If you have other ideas, I would love to hear. Okay, so now to the tips on how to present a paper in your seminars. So I would start, I think the most important thing that you need to get across in your presentation is what is the problem. I mean, the worst thing is to spend an hour where someone talks about algorithms and architectures and data sets and you don't even know what they're trying to solve. So take a whole 5 minutes if you need to, just to clearly state what is the goal of the paper. This will color everything else. And after you do that, do what the introduction of the paper does. Give the background. You sort of need to explain what the state of the field is, what approaches exist, and what's like the accepted way to solve this problem until now. And you need to explain that in order for the next part to be clear. What's special about this paper? What's the innovation? Like what's the innovative advancement that they present? So now just explain the main contributions. Very clearly, very in short, talk about what they actually built that's new and how does it improve something. And at this point, I think the most important thing for the audience to understand is how it all connects, especially when it's deep learning and architectures. People talk about like this one block that is new in this paper, but it's very important for the audience to understand what is the input, what is the output, how does it all connect all the way. Like, aim for clarity. The audience really will not understand all the details that you know in your head after reading the paper multiple times, but they will remember like the basic architecture and what was the goal there. Okay, after that, I suggest to take like 1 or 2 like highlights where you go into depth into something that the paper did. and like if there's a few innovations there, choose one of them and explain it all the way, so that people can like appreciate the depth of what's happening. You don't have to explain all of them, probably you won't have enough time. So explain the big picture and then dive into one or two things according to the time that you have. And finally, it's very important to look at the results and discuss them properly, like compare them to the other papers that are coming out. Is this actually a good result? A lot of the time, there will be a very smart method that does something with a lot of math behind it, and then the result is like 5% below state of the art. And that's not always, by the way, that's not always bad. That's how new methods, that's how new approaches begin, but it's good for us to know that. And finally, give your opinion. What do you think could have been done better? What was unclear? Where do you think this whole field is heading? Like, give something from yourself. I've added some more sources. By the way, this lecture, I believe, will be online, right? So you can read more about reading papers. And that's it. So if you have questions. Cool. Yeah.
I set up like 10 or 6 Google Scholar alerts, and then every week I get 60 minutes, and then often I notice that some papers are just really bad quality. Is there any way to filter out? It's often like, I'm not saying those are bad people, but it's like often like bachelor students trying to reinvent the wheel, and then they find out, oh, well, our method didn't really work, but
there's no magic solution. Basically, unalert those that you don't care about, that give you bad results. Skim really quickly. You basically can notice it in the abstract usually when you look at the results. They will say something like, we found a new approach, blah, 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 that gets similar to state of the art. That's a good sign that you should say, okay, unless it's something really interesting in the method, you can ignore it. But for now, I don't think there is a good signal as to...
Did you encounter this problem as well, or?
Definitely, yeah. But I just, I think already don't notice it because it happens so much. But I got really good at skimming. I think I skim tons of papers and just know which ones to dive into. Sometimes I might miss a good paper.